Hello everyone, my name is Andrew Davis, and today I'm going to be talking about superparameterization of sea ice dynamics using the Boltzmann equation. You can think of this type of model as a multi-scale model, which uses continuum models to capture large-scale dynamics and discrete element models to capture small-scale dynamics. So let's begin with some motivation, looking at some cool pictures of sea ice, and just state the somewhat obvious statement in this crowd probably that sea ice is a very dynamic material. In the top two figures, you see some nice pictures of sea ice, and you can see it kind of it has a lot of mechanical processes that are happening even in just these two pictures. It's obviously buoyant and floating on water. These rigid particles are bouncing off of each other. When they hit each other, they deform, they can fracture, and all sorts of other processes that are just very difficult to capture mathematically with physics that we don't really particularly well understand. In this bottom left picture, you see an image from the Mosaic expedition, which happened pretty recently, and you see all these melt ponds on top of the ice, which suggests there's some very complicated thermodynamics happening in addition to this mechanical forcing. And here on the right, we see the 2011 sea ice minimum compared to a historical median, and we can see that sea ice is declining quite rapidly in response to climate change, which has all sorts of global climate implications. Focus on modeling the mechanical processes that govern sea ice dynamics, which is incredibly complicated because sea ice can deform, it can fracture, there are these interacting flows, and there's all sorts of unknown and misunderstood physics. But kind of in a general sense, we can divide existing sea ice models into two categories, or maybe some sort of spectrum in between. On one extreme, we have continuum models, which also exist in some sort of hydrodynamic limit, where we think of averaged fields or average quantities over some small region in space. So things like a thickness field or a velocity field. And these types of models are very effective at capturing kind of large-scale dynamics, so think basin-scale, the entire Arctic. But because you're averaging over some small region, even in the limit of like grid refinement and really, really good numerics, you can't capture the small-scale dynamics because the model itself, the equations themselves kind of average out these small-scale effects. And additionally, because you're averaging out these small-scale effects, they're kind of subgrid effects, subgrid scale kind of physics that are happening. And because of that, you need to parameterize that physics that are likely not understood, but even if they are, they're not captured by the model using these non-physical constitutive laws or viscosity laws. And although these models have been quite successful, the effective viscosity is still a parameterization of a whole bunch of other physics. On the other end of the spectrum, we have discrete element models, which instead of modeling average quantities, track individual ice flows and models them as separate objects within the simulation that can interact with each other. And because of this, we're very effective at small-scale dynamics because we are explicitly modeling the small-scale dynamics. However, these models very quickly become computationally intractable for large-scale dynamics. You think over the entire Arctic, there are millions of floes, lots and lots and lots of floes, and so just tracking those that large number of flows becomes computationally just not possible, even with parallelized models and very big computers. And additionally, sea ice flows aren't rigid particles that are just bouncing off each other. They can melt, they can freeze together, they can deform, and they can fracture. So you kind of need this continuum model within each sea ice model, which in addition to just compounding the computational expense, really requires a lot of physical models that we don't really have. But kind of largely, we think of the continuum models as existing in some sort of hydrodynamic limit, using a lot of models that look a lot like fluid dynamics or maybe deforming solid type models. And then the discrete element models we think of as being in a kinetic limit, where at your core, you're really solving like F equals ma or Newton's second law using rigid particles that are interacting. And so our goal is to try to find some sort of intermediate type of model, which really is using these ideas from hydrodynamic models to capture the large-scale dynamics, but then use a kinetic model at the small scale to capture these small-scale dynamics and somehow combine them in a way that preserves the things that we like, modeling both large and small scale, but is computationally feasible for large-scale dynamics. Before we talk about the specifics of our approach, I want to talk about some previous work that's been done to combine the hydrodynamic and the kinetic limits in modeling. The first is an iterative approach between finite element methods and a small-scale discrete element method, where you attach to each finite element quadrature points a discrete element method. So at each time step, the first thing that you do is update your finite element method macro scale solution. Then at each DEM, you pass the local solution to that DEM. You assume some sort of small scale time evolution for the small scale model, and that it's an instantaneous steady state. So you update your model and you run it to steady state. Then you compute the average stress that each particle in your DEM feels, and this is called the homogenized Cauchy stress tensor. And you use this stress tensor as your constitutive law to update your finite element method, and then you just iterate through time. So this is a nice approach if you have this time scale separation in your models, to use both the discrete element method at the small scale and a finite element method at the large scale. And it has this added benefit of, given the solution to the finite element method, the discrete element methods are embarrassingly parallel, so you can leverage a lot of large computing power. The second approach are these super-parameterized atmospheric models, which are basically a multi-scale approach where you run these large-scale atmospheric models, which have a lot of subgrid dynamics, like very small-scale turbulence and cloud formation and stuff like this, that the large-scale model can't run. So you just you run a small-scale model within each grid box to capture these subgrid scale dynamics, but you include these additional relaxation terms, which aren't physical. They just penalize deviation between your small-scale model and your large-scale solution, so that the small-scale model kind of relaxes toward the large-scale solution. And these relaxation terms are more heuristic, and a lot of the numerical couplings between these models are heuristic because the goal is to capture observed dynamics more than to be mathematically rigorous. And that's not to say that there aren't many papers on this approach that are incredibly rigorous, but the goal is more of a heuristic motivation than it is a mathematical one. And then the third approach is a more formal multi-scale analysis using techniques like change of variables or fast and slow coordinate system or boundary layer analysis, which if anybody's taken a fluid dynamics class, everybody knows that these types of approaches are very, very rigorous, but also incredibly technical and incredibly difficult to derive. However, they have this huge advantage that once you get through this very technical details, a lot of times things like the relaxation terms in the super-parameterization or the exact form of the coupling for the finite element method and the DEM become very, very clear, and they either justify a lot of these heuristic choices that we're making, or they have very strong indications of what some of these seemingly arbitrary choices should be. And that's kind of going to be our approach, is we're going to use a formal change of variables and this very formal analysis to justify a lot of the heuristics that have already been done in these two other previous works. And then we're going to, that's what we're going to do. Okay, so just to remind you, our goal is to derive a kinetic model, or a model that uses some sort of kinetic theory, at least at a small scale, to generalize a lot of the more typical hydrodynamic models that are currently being used to model sea ice. And the hydrodynamic models are more designed for large-scale dynamics. So we're going to start from a slightly different place than is typical for a sea ice model, and that is we're going to begin by assuming that we can model sea ice using what's called a Boltzmann equation, right? And this is a little bit different in that instead of modeling the ice over just space and time, we're going to have a coordinate system that includes space, time, and also velocity. So the velocity is not an unknown in our system. It's actually an additional coordinate system. So our PDE is going to be defined over a 2D plus 1, so space, velocity, and then an additional time dimension, right? So that's going to be kind of where we start in this somewhat strange coordinate system. And instead of trying to model things like sea ice thickness or a velocity field or energy or something like this, we're going to model the probability of observing sea ice at location x with velocity v. So the unknown, the quantity of interest, is this probability density function, which I'm denoting by pi, or this joint density function over space and v. And again, this is the probability of ice being at location x and with velocity v. And in addition to this joint density over the full space, we're going to define two other densities. The first is the marginal density, mu here, and this is, we're going to call it the mass density. And to derive the mass density, we're just going to marginalize out the velocity coordinates. We're just going to integrate over the velocity coordinate. And that we interpret the mass density as if we take some set, some physical space. So this is like a subset of the Arctic, maybe it's some basin, or we could even say it's the full Arctic if we say it's our full spatial domain. If we integrate over this space, then the mass density is the amount of ice independent of velocity. It's just the amount of ice that is currently inside this set E. And so the second density that we're going to care about is the velocity density, which we're denoting nu. And so the velocity density is just the conditional density defined by the law of total probability, so that nu times mu is equal to this joint density pi, right? And the way we interpret the velocity density is at a specific point x, nu is basically the distribution of possible velocities that the ice at that point might have, right? So if the ice is at rest, right, this is a delta distribution at 0. So the ice is just sitting there and there's no chance that it's moving at all, right? But maybe if ice is moving around, or maybe there's some uncertainty, if there's a probability distribution, this is basically the probability that ice at location x is moving at velocity v. Okay? And so the distribution pi, this joint density that we're going to end up caring about, evolves according to this equation here, which is called the Boltzmann equation, right? And so this is a dynamic problem. The joint density can change in time. And then we have two advection terms. The first is this operator grad x dot v times this density here is basically the material, or this probability density, being advected by the velocity coordinate around around space, right? So this is going to be a very familiar advection term. It pops up all the time in continuum mechanics. The second advection term here is very similar in intuition, except for instead of the density being advected around the spatial domain, we can say that this density is also being advected around the velocity coordinate, and it's being advected by the acceleration term, right? And this acceleration term is some field that we as users have to prescribe. And so the acceleration typically will be due to ice-ocean or ice-atmosphere interaction, and it'll be some sort of, for example, quadratic drag term, where as winds blow across the ice, they blow it around, they blow the density. This drag creates an acceleration, which then moves moves the density around the velocity coordinate. And then on the right-hand side here, we have the collision operator. And this collision operator, you can think of this as some sort of integral operator, maybe some sort of kernel operator that acts on this joint density of the location and velocity of ice. And basically, it's a local operation, so the integral is typically only over the velocity space. And it's basically these co-located particles. So if two particles of ice or two ice floes are very, very close to each other, or in some idealized world at the exact same point, then they're colliding, and these collisions can transform this velocity density. Can transform this density in the velocity space locally, and it models things like floe-floe collision, ridging, fracture dynamics, and all these very complicated physical processes are kind of wrapped up in this collision operator. So this Boltzmann model is going to be our starting point, and we're going to use this model to first derive a macro-scale continuum mechanic equations, which will look very similar to previous CIS models. And we're also going to use a small-scale model to simulate this velocity density at key points around the domain. Okay, so given that our starting point is the Boltzmann equation here in the middle, our next step is to derive these macro-scale conservation equations. And the form of these conservation equations is going to look very familiar. In fact, it's exactly the same to the conservation equations that are typically used for sea ice model. We're just going to derive them given the Boltzmann equation. And the way we do this is simply by integrating over the velocity space. We're going to integrate the Boltzmann equation over the velocity space, but first we're going to multiply by some arbitrary function of the velocity coordinates, an arbitrary function of v, and depending on the choice of this function, we can derive a different equation, right? And so the two most useful for our purposes are going to be choosing the constant, this phi equals 1, and then this linear equation that phi equals v, right? But we could say something like phi equals 1/2 norm v squared, and that would derive the energy conservation equations. And you can continue this pattern to drive higher moments in different conservation equations for other conserved quantities. But for now, we're just going to consider mass and momentum conservation, right? So if you, given these choices for phi, plugging them into this integral and doing a bunch of algebra under some very mild assumptions, things like this density pi can't have any deltas, right? So we're assuming some relatively smooth density. So under these relatively mild assumptions, we end up at these mass and momentum conservation equations, right? And these look very familiar. You have your time derivatives, and then you have this advection term, so your mass is being advected around by some expected velocity u, and then here again you have your momentum being advected around by some expected velocity v, u, and then you have some sort of matrix is sigma here. And in typical models, right, this matrix is your constitutive law, right? So you assume some stress strain relationship, for example, or maybe some sort of effective viscosity or some sort of other sort of parameterization like that. And you plug that assumed material property in for sigma, and then you can solve these equations, right? And this f here is some sort of expected, some forcing function, right? So maybe the drag term or something. It would depend on like the ocean velocity and the atmospheric velocity and things like this, right? But in this model, where these equations come from the Boltzmann equation, we have expressions for these terms in terms of the conditional density nu. So in particular, the velocity coordinate, so the macro scale sea ice velocity is actually the expected velocity, right? So if we take the expectation over the velocity coordinate with respect to this distribution nu, we get this expected velocity u. Right? And so because we have two equations, we actually have an equation we can explicitly solve for this expected velocity. So this is okay. Now, instead of prescribing a constitutive relationship, however, we're going to say that sigma, this matrix here, the stress tensor, is equal to the covariance of the second moment of the velocity density nu here, right? So it's the expectation of this term here, right? And so unfortunately though, we don't have a way of explicitly evolving this matrix, right? We don't have an equation for this moment. So this is actually an unknown quantity because we don't know this density nu, right? And similarly, right, the external forcing is actually the expected forcing. So it's the expected acceleration times the mass, right? So mass times acceleration is force, right? But again, we have to take this expectation over this unknown density nu, right? So these equations aren't closed, right? These two quantities in red, the covariance matrix here and the expected forcing are unknowns, right? And maybe we can make some sort of assumption about the form of the forcing matrix, the macro scale forcing, right? And say like we don't really need to know this expectation exactly, but this covariance matrix is really going to be quite troubling, right? We really need to know this covariance matrix in order to evolve these equations, right? So we're going to use finite volume or discontinuous Galerkin or some sort of finite element method to solve these macro scale conservation equations, just like you would typically see in a sea ice model. But in addition, we're going to use a particle method at key points in the domain in order to evolve some sort of Monte Carlo approximation of this covariance matrix sigma and this expected forcing f. Right? So our next step, having derived the conservation equations, is to figure out how this conditional density nu evolves in time and figure out how we can represent that in some sort of numerical way. Okay, so our next step is to determine how this conditional velocity density nu will evolve at some particular point x. So we have our original Boltzmann equation here, and all we're going to do is substitute in this decomposition for pi. So this is just a law of total probability that pi is equal to the marginal density mu times the conditional density nu at some specific point x. And then we're also going to substitute in for the time derivative of u. This is just the mass conservation equation, right? And we've rearranged it into this form. So given these substitutions and plugging them into this evolution equation, we end up at this conditional evolution equation, which says how some point, how this function, this probability density function, nu will evolve. And it has these four terms here. The first is the relaxation term, right? And the relaxation term basically penalizes deviation from the expected velocity u. So if nu, this probability density function over the velocity space at some point x, has a large probability at the coordinate v, then this term will be quite large, the relaxation term, especially if that particular choice for v is very far away from the expected velocity u, right? So we're penalizing deviation from the expected velocity. And the strength of this relaxation is determined by the gradient of the mass density, or maybe more specifically, the gradient of the log mass density. And so for a steeper log mass density, we're going to have a stronger relaxation term. And so these relaxation terms, or similar types of relaxation terms, are used in a lot of multi-scale and super-parameterized model. And here we're showing that these relaxation terms actually come up when you do out this analysis and you try to derive these equations more rigorously. So this next term here, the collision term, basically says that the small scale model sets some point x, this integral operator over the velocity space, this rearrangement of this density nu due to small scale interactions becomes important. If you recall in the conservation equations, this term actually went away, but we can't neglect it when we're looking at the evolution of the velocity density. So then the next term here is the acceleration term, and this is just an advection around the velocity space. So this prescribed external acceleration is advecting the velocity mass density around the velocity space. And then the final terms here are the coupling terms, and these are the ones that are going to be difficult for us to address. And the reason is because what they are though, is that they account for mass coming in or going out of some specific point x due to advection in the spatial coordinate. So this term here is basically the compressibility of the macro scale expected velocity field. So if this divergence were non-zero, then at that point x, you have mass either entering or leaving the domain because of the convergence or the divergence of the expected velocity field, and that needs to be accounted for in this conditional density. And similarly, this is just an advection around the spatial domain at a specific velocity coordinate v. So these couplings terms are difficult because they depend on, or specifically this one, depends on gradients of the velocity density with respect to x. And because of that, this entire equation is still a probability, this is still a PDE in space, velocity, and time. So this is still a 2D plus 1 dimensional PDE, which is just as difficult to solve as the original Boltzmann equation. So what we're going to do is define a change of coordinates so that we can neglect these coupling terms. And the idea is that if you have two microscale models, so we're going to have two particle methods that are attached to nearby points x1 and x2. And if those points are nearby in this coordinate system here, we're going to define a new coordinate system, and in this transformed coordinate system, we're going to push those 2 points to be really, really far apart. And because they're so far apart in the transformed coordinate system, we can neglect the coupling terms, and that will, with relatively minimal errors, and then we're going to solve the equation in that transformed coordinate system and transform back into the original coordinate system. And we're going to show that when we do that, the error that we incur is relatively minimal. And we have some sort of parameter that can control how small it actually is. Okay, so we need to evolve this conditional density over some small time window t hat to t hat plus delta. Right, so to give some context, recall that we're solving these conservation equations on the macro scale, which only depend on the spatial domain, and that for each time step of the discrete version of the conservation equations, we also need to update this conditional density at particular points that we scatter around the domain that we're free to choose. And the big challenge that we're going to have to deal with is the fact that these points are scattered around the domain, and because of these coupling terms, any specific one of those points where we care about the conditional density nu is going to be coupled with its nearest neighbors, and because we need to evaluate the spatial derivative here. Now, so we're going to define in a second a transformation that allows us to neglect these coupling terms. But before we do that, I want to address this collision operator. Now, so far in this talk, and also for basically the remainder of this talk after this slide, we're really just going to say this is just some black box operation, which is like a discrete element method at a specific point x hat, and it's very, very local. In fact, probably well approximated by assuming that these ice flows are all basically at the exact same location and interact very often. And this discrete element method can be arbitrarily complicated or arbitrarily simple. So on the complicated end of the spectrum, you can have flows that are bouncing off each other, that are fracturing, and that can ridge on top of each other, and all sorts of very complicated dynamics. And on the other end of the spectrum, you could just have point particles that bounce off each other due to some sort of elastic contact law. And so for all of my examples that I show in a second, I'm going to assume this very simple elastic contact law. But you can just imagine this as a black box discrete element method. And so the way we address this collision operator is with a method called operator splitting, where what we do is we define some new density, nu prime, and we initially, at the beginning of this small time window, we just set its initial condition equal to whatever we have stored already for this density nu. And then we integrate nu prime using only the collision operator. So we ignore the coupling terms, the acceleration, and the relaxation terms, and we just integrate over this small time window using the collision operator. And because the collision operator doesn't rely on any derivatives of nu, we can do this independently for all of our DEMs across the entire spatial domain. And then once we've done this first pass through this integration over this small time window, we'll reset the initial conditions for nu to be equal to the final conditions at the end of the small time window of nu prime. And then we're going to integrate again, but this time we're not going to use the collision operator. So it's kind of an iterative method where you update the macro scale equations, you do your operator splitting where you do your DEM simulation using your collision operator, and then you repeat the small time window integration for each small scale model without the collision operator. So what this is going to do is introduce the acceleration term and also introduce a relaxation term to kind of revert back to what you would expect given your macro scale solution. You'll also notice the second time around we reintroduce the coupling terms. So now we need to define this change of variables, which is going to allow us to neglect the coupling term. In order to find a change of variables that allows us to neglect the coupling terms in this conditional evolution equation, we're going to first define some parameter delta, and this is the time step size for the macro scale model. So after we've discretized, we're going to be taking steps of size delta. Or really, it's just some small time window over which we need to integrate our conditional evolution equation. And we're going to use this small parameter delta to define a change of variables over time, space, and the velocity coordinate. So this here just says that the small time window beginning at t hat to t hat plus delta in this new coordinate system is going to go from 0 to 1, right? So so an order 1 change in t leads to a small change in the original time. This is our spatial transformation, right? So we're gonna be specifically focused on one point x hat, and if we vary x, we're gonna be moving around this fixed point x hat. And then we're also going to include this velocity term here, right, to move us into this Lagrangian frame. So our original coordinate systems are an Eulerian coordinate system, and now this transformed domain, we have this Lagrangian coordinate system. And we're going to define this big x, this new coordinate centered at x hat. And now we're going to scale it by this 1 minus c. And we're going to show in a second that c has to be greater than 1. So a small change, or an order 1 change in x, actually leads to potentially quite a large change in this x hat. Or quite a large change moving away from this fixed point x hat. So we're going to have to be very careful in how we choose c. And I'll get into the details of that in a second. And then finally, we're just going to say that our new transformed velocity is exactly equal to our previous velocity. So importantly, what we've done is taken this small parameter delta. We've defined a change of variables over a small time window that has moved us from an Eulerian frame to a Lagrangian frame. And when we apply this change of variables to this term here, the new conditional evolution equation for the density specifically at the point x hat turns into this equation here. So now, again, we have the exact same set of terms, the relaxation term, the acceleration term, and the coupling term. But now what we can do is neglect the coupling terms over this small time window t hat to t hat plus delta. So maybe a more graphical way of looking at it is that we have this change of variables, and this cartoon here shows the original coordinate system. So if the vertical axis is somewhat in a cartoon type of way the spatial coordinate, and then each of these planes corresponds to the velocity coordinate, the distribution that we care about is the plane that's associated with specifically x hat. So this gray coordinate system, or this gray plane here. And this is the density that we want to evolve. And then in the transformed coordinate system, because we've moved into a Lagrangian frame of reference, this thing that we care about, this gray plane that we care about, turns into this tilted plane here. And so this region, this manifold, this planar manifold, corresponds to this region here in the original coordinate system. And what we do when we neglect the coupling terms is we actually define a new density that's on a plane in the transformed coordinate system, specifically the plane x equals 0, this transformed x equals 0. And when we transform back after we've done our time integration over this small time window, we end up with a plane in this red plane in our original coordinate system, which is the density that we've actually computed. And the error that we've incurred because of neglecting this coordinate system is somehow related to the slope of this plane, right? So if we had no slope, then we'd have no approximation. And what we can show is that the tilt in this plane in the rescaled coordinate system is actually equal to this quantity here, delta c to the times t. So we need it to be a relatively small time window. So t is order 1. And then the error is something like delta c, so that as our small time window goes to 0, so this macro scale time step parameter goes to 0, the error also goes to 0. So this transformation that allows us to neglect the coupling terms in some transformed Lagrangian domain is the last ingredient that we need to define our entire superparameterized algorithm to solve the Boltzmann equation. So what we're going to do is at each time step for the superparameterized algorithm is to integrate over this small time window from t hat to t hat plus delta. And so step 1 is to update our macro scale fields. So in our case, we're going to be using a finite volume or a discontinuous Galerkin method, depending on the numerical parameters, to update the macro scale field. And then given these macro scale fields at key points scattered throughout the domain, we're going to integrate the conditional evolution equation for the velocity to determine the distribution in the velocity coordinate. And this is a two-step process. The first is the collision step, where at these key points in the domain, we just apply some discrete element method to model the small scale floe-floe interaction for sea ice. And then the second step is this convection step, where we're integrating these rescaled equations, which includes the relaxation term, which basically says the DEM must somehow be similar in some way to the macro scale solution. And then finally, given that we have all these small scale models scattered throughout the domain, we need to interpolate expectations with respect to this previously unknown distribution nu, so specifically the covariance of nu and the expected acceleration onto the spatial mesh. And basically, as we add more and more small scale domain models into our simulation, this interpolation becomes more and more accurate. And then we just iterate over time, applying this transformation over small time windows until we hit, t equals 1 or whatever. So the main result that we have from our analysis is that if pi is the true solution to the Boltzmann equation, and pi brev is the approximate solution, so the solution that we get by solving our model, neglecting the coupling terms in the rescaled domain, we can actually prove and we can bound that the total variation, so the error between these two distributions, so our true distribution and our approximate distribution, is bounded by some function g of delta, where delta is this parameter, the small scale time window, and we can show that g of delta for any finite time goes to 0 as we refine as delta goes to 0, so as we take smaller and smaller time steps. So this method is asymptotically exact in the limit of small time steps. And this error bound does assume that we have exact numerics, so I don't take into account things like the finite volume or the finite element error. So there's going to be some sort of additional term because of your mesh discretization in your error. But we can actually have a closed form solution for what the error is because we neglect the coupling term. To recap, what we've done is developed a way of numerically solving the Boltzmann equation using this super-parameterized approach, where at the macro scale or in some sort of spatial domain, you're solving a conservation equation for the momentum and the mass density, or equivalently the mass density and the expected velocity. And then at the same time, we've coupled those conservation equations with particle methods that are scattered around our domain to estimate expectations with respect to a velocity distribution, which is a conditional velocity distribution at those specific points. And by coupling these approaches, we have this rigorous method of solving the Boltzmann equation, or numerically solving the Boltzmann equation. And this will motivate kind of a super-parameterized approach, or a multi-scale approach that combines a discrete element method with these large-scale conservation equations over an entire Arctic domain, for example. So to first, we also have this theory that basically proves that as the time step of the conservation equations goes to 0, that we're actually recovering the Boltzmann equation. So just to confirm this numerically, the first thing I'm going to do is show results where what you're looking at here is a simple square domain. Initially, we start with a constant mass density, and we're going to have constant forcing, external forcing, that's going to push all of the mass to the right. The mass is going to build up. The gradient is going to, the mass gradient is going to create a force that goes to the left, and you're going to see this sloshing type effect. And so if I play this, that's exactly what happens. We get these velocities that build up mass to the right, and then that gradient in the mass creates a sloshing effect that goes to the right, and the mass just kind of sloshes back and forth throughout the domain. And so the nice part about this simulation is this all lives in a limit where we would expect the Boltzmann equation to be completely solved by the compressible Euler equations, and you'll notice this is exactly the same solution that we would expect from the compressible Euler. Slightly more interesting simulation or numerical result that I want to show is starting from an initial condition where we have some chunk of mass in the middle of our domain that's surrounded by a relatively small amount of mass. So there's basically no mass in the exterior and a lot of mass in the interior. And we just prescribe some divergent flow, so the external forcing, that is going to pull this mass apart. And when I run this, you'll see that this mass just gets pulled apart, and I'll just stop it here for the sake of discussion. So in this case, all of the fuzziness that you see is actually a numerical diffusion. So that's something that we are addressing right now in our code. But the fact that this mass is being pulled into two separate chunks is promising, because unlike a lot of more traditional material science, which requires this continuity between this chunk of mass, we're actually able to pull it into discrete parts, just like maybe we'd be able to pull an ice floe into discrete parts. So this is a very promising result that this type of model might be well suited for modeling sea ice. So I'll just finish the simulation. You'll see these chunks of mass are going to hit the boundary and then bounce off the boundary and kind of interact with each other again. You did see a little bit of artificial oscillations due to some numerical issues. I have actually been able to solve that problem on the numerical side. I just haven't been able to run those results yet, because these are quite expensive simulations. So probably by the time you're actually listening to this, I'll have much cleaner results. In conclusion, what we've done is coupled large-scale conservation equations with small-scale particle methods that are scattered around our spatial domain, and we've used this coupling to solve the Boltzmann equation. And in this effort, we've rigorously derived a super-parameterized approach, which uses these relaxation terms in the small-scale models that are very similar to relaxation terms that are used in other super-parameterized schemes. The key difference here in this case is that our relaxation terms are justified by this rigorous change of variables. We've also been able to prove that our scheme exactly recovers the Boltzmann solution, or the solution to the Boltzmann equation, in the limit of this parameter delta, which is the length of some macro scale time step. And we've been able to show that this exactly recovers the Boltzmann solution in the limit that parameter goes to 0. And then we've also been numerically able to show that this scheme recovers desirable dynamics. So in some appropriate limit, we recover the compressible Euler equations, but we also get some suggestive results that maybe we can cover some non-trivial dynamics that we observe in sea ice. And so our future work and the kind of things that we've probably done by the time you're listening to this talk is able to confirm the numerical results, so just go through the code more rigorously and make sure that everything is correct, and then implement simulations that maybe have more complicated external forcings or things that maybe look a little bit more like sea ice, just to see how this type of model will behave under more complicated scenarios. So thank you for listening. I look forward to discussing. If you have any questions, feel free to email me, and I'm looking forward to this workshop. Thank you.